Good morning dear learners, I am Dr. Poddar, faculty of Bhila Institute of Technology, Durg. I welcome you all in this today's lecture session. We will learn about satellite communication system architecture. Satellite communication system architecture comprises of approximately 12 segments that begins with the space segment, ground segment, user segment, link segment, communication network, frequency band, modulation and coding, multiple access technique, protocol and standard, security and encryption, and auxiliary systems. In space segment, satellite is the major component. Satellites are placed in orbit around the earth and serves as relay station for communication signal. They receive signal from earth station, that is uplink, amplify them and transmit them back to different location on earth, that is called downlink. Satellites are majorly of two types. One is spin stabilized satellite. These satellites maintain their orientation by spinning around their axis. Spin provides gyroscopic stability which keeps the satellite oriented correctly. The spin rate is typically controlled using thrusters or reaction wheels. Then another one is 3-axis stabilized satellite. These satellites use combination of gyroscope, reaction wheels and control movement gyroscopes CMGs to maintain a fixed orientation in space. They can precisely control their pitch, yaw and roll axis, allowing for more accurate pointing of antennas in and instruments. Then in space segment there is a power supply subsystem. Power supply subsystem mainly comprises of solar cell and rechargeable batteries. Functions of solar cells are to convert the sunlight directly into electricity through photovoltaic effect. They are mainly source of power for satellite. Common types of solar cell used in satellite includes microcrystalline silicon cells. They are high efficiency and long lifespan. Gallium arsenide cells, higher efficiency compared to silicon cell and better performance at higher temperature. Then multi-junction cell, made up of multiple layers of different semiconductor material. They can capture a wider range of solar spectrum, offering the highest efficiency. Configuration: solar cells are arranged in arrays or panel so that they can form a matrix type of arrangement and can be deployed once on the satellite and the satellite reaches in the orbit. These panels are usually mounted on rotating structure that they keep them oriented towards the sun. Then rechargeable batteries. The function of rechargeable batteries are to store the electrical energy generated by solar cells and provide power when the satellite is in earth's shadow, that is called eclipse period, or during the period of high power demand. There are common types of rechargeable batteries used in satellites. They include nickel cadmium batteries. They are very reliable and have been used for many years, but have low energy density and suffers from the memory effect. Then nickel metal hydride batteries. They are high energy density than nickel cadmium, but less prone to memory effect. Lithium ion, high energy density, high weight, no memory effect. They are most commonly used batteries in modern satellites. Battery management are managed by power management and distribution system, that is called PMAD, that controls the charging and discharging cycles to optimize the battery life and ensures the reliable operation. Eclipse period. The eclipse period is the time duration which satellite phases through the earth shadow and not illuminated to the sun. During this period, satellite cannot generate power from the solar panel. Now, this eclipse duration, right, for geostationary satellites, it is 70 minutes per day, and for low earth orbit LEO satellites it is 30 to 40 minutes. Now, this eclipse period is very crucial, because in case of rechargeable batteries, the minimum charge should not go below the threshold value. So, when the batteries are selected or mounted, so this care has to be taken. Power management and distribution system, that is called PMAD. The PMAD system is responsible for regulating and distributing the power generated by solar cells and stored in the batteries. It ensures that all satellite subsystem receives a stable power supply. In satellite technology, the different parts of satellites, they are known as subsystem. So, all the subsystems of satellite, they get the power from these. So, main functions of these are the voltage regulation, power prioritization. So, whenever if a certain subsystem need a high power, so that subsystem should get the power on priority. Battery management, load shedding are the functions of PMAD. Now, to understand the functions of this power supply subsystem of satellite, let us discuss a numerical on this topic. So, problem says Intelsat 4A generation of spacecraft used solar cell wrapped around a cylindrical drum of 2.38 meter in diameter with the height 2.9 meter. The drum was rotated at 60 rpm to spin stabilize the satellite, and at the end of life, which is abbreviated as EOL, the solar cell were designed to deliver 708 watts of electric power. So, this data is given in the problem, and based on that it is asked to calculate the efficiency of solar cell at the end of life. Consider a standard incident solar power of 1.39 kilowatt square meter. In second part, it is asked if the cell is degraded by 15% over the lifetime of satellite, what was the beginning of life output power. Then in third part, it is asked how much electrical power was dumped into load register at the beginning of life if the margin of 80 watt was provided at the end of life. And in the last fourth part, it is asked if the spinner design has been replaced by 3 axis design, the rotated to face the sun all the time. So, what area of solar cell would have been needed? So, these 4 things has been asked to calculate. So, let us begin. First, we will find out the area of cylinder, right. The formula is to calculate the area of cylinder is pi d h, where pi is the standard, d is the diameter of the drum and h is the height of the drum. D and h is given, so that we can fill directly. Then for cylindrical satellite, the area exposed to sun is 1/3 of the total area. So, just dividing by 3 the area of cylinder, we can find out area exposed to the sun, and then we can calculate the total input power, that is incident solar energy or solar power, that can be called as flux density into area exposed to the sun. So, this gives the total input power as 10.11 kilowatt. After that, we can find out the efficiency. Efficiency is output power to the input power. Output power is given, input power we have calculated. So, efficiency of satellite comes out as 7% at the end of life. Then in part B, right, part B efficiency at the beginning. So, let us say the x is the efficiency at the beginning with now it is said that consider 15% degradation at the end of life. So, x will become 0.85 x and that will equal to the 7% efficiency of end of life efficiency. So, with this relation we can find out the value of x. So, that is the efficiency at the beginning of life and it comes out as 8.23. And again using back the efficiency relation where efficiency is equal to output power to the input power. Now, we will put the value of efficiency at the beginning, the input power, and with this relation we are able to find out the beginning of output power. So, that will come out as 832 watts. Then in part C it is given end of life margin, says the 80 watts has to be considered, it is given. So, with the margin end of life power will be 708 plus 80, that is 788 watts. Now, taking 15% degradation at the beginning of life. So, it will be 788 divided by 0.85. So, with 15% degradation the power at BOL, that is beginning of life, will be 927. So, we can find out the extra power just subtracting 708, that power at EOL from this 927 watts, that is the power at BOL. So, it comes out 139 watts. Now, at the most 708 watt and the extra power is available at the end of life is 927 watts. So, the dummy load which has to be dumped in is 927 minus 708. So, 209 watts, this much power has to be dumped into the dummy load. This is the answer of part C. And in the last part it is asked that if the spin structure is replaced by 3 axis structure. So, find out what is the extra area is required. So, the effective area for spin structure that we have calculated is comes out 7.27 square meter, and we know that this area is generating 708 watt at the EOL. Now, considering the 10% degradation in the conversion efficiency of the solar cell, because in 3 axis the solar panel, complete solar panel is continuously exposed to the sun. So, because of the 10% degradation in the conversion efficiency. So, what we will do, we will just divide the 7.27 by 0.9 considering 10% degradation. So, this will give the extra area, that area comes out 8.07 square meter. So, this problem gives the better insight to the understand the power supply subsystem of satellite communication system architecture. Then another subsystem is attitude control in satellite. Attitude control system are essential for maintaining the correct orientation and position of satellite in space. This ensures that the satellite's antenna, sensors and other instruments are accurately aligned with their target area on Earth. There are two primary methods of stabilizing a satellite's attitude. One is spin stabilization and another is 3 axis stabilization. In spin axis stabilization, how the orientation is fixed for the satellite. In this case, satellite is rotated at a very high speed in a particular orbit, and thereby the orientation of satellite is fixed. Another one is 3 axis stabilization. 3 axis stabilized satellites maintain their orientation using active control system that can adjust the satellite orientation in 3 dimension: pitch, yaw and roll. Arrangement and components. Reaction wheels, these are the flywheels that can spin in different direction to create the torque and adjust the satellite orientation. Control movement gyroscope, CMGs, advanced gyroscope that provide precise control over the satellite orientation. Gyroscope measure the satellite orientation and provide feedback to the control system. Star tracker, optical devices that uses star position to determine the satellite's orientation. Sun sensors detect the position of the sun to help the maintain orientation. Magneto-torquers, electromagnets that interact with the earth's magnetic field to adjust the satellite orientation. Thrusters, small propulsion units that can provide fine adjustment to the satellite orientation. How it works? Reaction wheel and CMGs. Reaction wheel spin the opposite direction of the desired rotation to create a counter torque that adjusts the satellite orientation. CMGs can change the orientation more precisely by adjusting the direction of the flywheel's spin. Feedback loop, gyroscope, stars trackers and sun sensors provide continuous feedback on the satellite orientation. This information is used by the onboard control system to make necessary adjustment. Active control, the control system continuously adjusts the reaction wheels, CMGs and thrusters to maintain the desired orientation. This active control allows for precise pointing of antenna, cameras and other instruments. To summarize, attitude control system are crucial for successful operation of satellite. Spin stabilization provides a simple and reliable method of maintaining orientation through gyroscopic effect. In contrast, 3-axis stabilization offers precise and flexible control using reaction wheel, CMGs and other sensors. Each method has its advantage and is chosen based on specific requirement of satellite mission. Then another subsystem is telemetry tracking and control system. Telemetry tracking and control system are essential component of satellite communication system, enabling the monitoring and management of satellite. TTC system consists of both space segment on board the satellite and ground segment on earth that works together to ensure proper functioning of and controlling of satellite. Telemetry subsystem, sensors and instruments. There are thousands of sensors that are on board on the satellite, and what they sensor do, they continuously scan the all the datas, right, all the physical parameter for which the sensors are there, and they collect this data, give to the encoder, it encode, and after encoding it give to the telemetry transmitter. Then through telemetry transmitter, this encoded data is sent to the earth station control room, and in the earth station control room they compare the received data with the standard set value. If they found any discrepancy in this, then they generate a corrective command. Now, this corrective command is sent back to the satellite, then satellite receives this command, right, decode this command and is stored, and after that once again satellite send the received command back to the earth station, and in earth station control room they check whether the command received by satellite is correct or not. If the command received by satellite is correct, then from earth control station command execution signal is sent. On receipt of command execution signal, the stored command in the satellite is routed to the particular communication subsystem and the correction is done. This care is taken because the due to the distance, right, the signal has to travel more than 36,000 kilometers in the harsh environment. So, signal, there is a chance that satellite may receive a wrong signal. So, this care is taken to ensure that the satellite has received the correct command. So, this is how the telemetry command system works. In the ground segment, just I told you, we have antenna, we have tracking system, we have control system to perfectly control all the subsystem of satellite. Then we have another network operation center, that is abbreviated as NOC. Central control, the NOC coordinate all TTC operation including tracking, telemetry analysis and command transmission. Here I will tell you, this telemetry signal is not the communication signal. Telemetry signal is a controlling signal that is used for the controlling purpose, and communication signal is different, that is handled in the communication subsystem, which we will discuss just now. So, NOC plans satellite makeovers and operation to ensure optimal performance and the longevity. Anomaly detection and resolution, the monitors for any anomalies or issue with the satellite and takes corrective action as needed. So, to conclude, the TTC telemetry tracking and command subsystem or telemetry tracking and control subsystem, TTC is very vital for successful operation of satellite communication system, providing the necessary tool to track, monitor and control satellite throughout their mission by ensuring continuous communication between satellite, that is space segment, and the ground station, that is ground segment. TTC system enables real time monitoring and management, contributing to the reliability and effectiveness of the satellite operation. Then coming to the very important, that is communication subsystem. Communication subsystem is also known as transponder. Operation of this system is very crucial, because this is the earning part, whatever expenses that we have done on the satellite. So, this is the subsystem from which the earning is done. So, communication subsystem, which is also known as transponder. So, transponder is a crucial component of satellite communication system that receives, amplifies and retransmits signal between the ground station and the satellite. The transponder performs several key functions to ensure the integrity and the quality of communication link. It does the signal reception. For that, antenna is there, right. The transponder receives the incoming signal from the ground station through satellite receiving antenna. Then there is a frequency down converter. The received signal is often at high frequency, that is for example, C band and Ku band. The frequency down converter converts the high frequency signal to the low intermediate frequency to facilitate easier processing. Then amplification. In satellite technology, right, as the signal has to travel a very long distance, so signal becomes weak. So, in satellite technology we have to work under the weak signal condition. So, that is why the conventional amplifier is not suitable in our satellite technology. We have to use low noise amplifier. So, this abbreviated as LNA, the down converted signal is passed through LNA, which amplifies the weak received signal while adding a minimal noise. This ensures that the signal is strong enough for further processing. Then there is a gain control, AGC is there, that may be used to maintain the signal at consistent level, preventing the signal distortion due to variation in the signal strength. Then frequency conversion and filtering is done. After amplification, the signal undergoes a frequency translation to the designated transmit frequency band. This involves the converting in IF back to the higher frequency suitable for transmission. We make the use of band pass filter. And finally, in communication system, the power amplification is there. So, high power amplifier is there, right. The modulated signal is then amplified by a high power amplifier such as TWTA, travelling wave tube amplifier, or a solid state power amplifier. This step is crucial for ensuring the signal is strong enough to be transmitted back to earth over a long distance. There are the types of transponder: bent pipe and regenerative transponders. That has its own advantage and drawback. Bent pipe is simpler, whereas the regenerative can improve the signal quality by removing accumulated noise and the errors. So, to conclude the working of transponder, a transponder in a satellite communication system receives signal from the ground station via its receiving antenna, down convert the high frequency signal to an intermediate frequency for processing, and amplify it using LNA, low noise amplifier. The signal then undergoes frequency translation to higher transmit frequency and filtered to remove unwanted noise. In regenerative transponder, the signal is demodulated to baseband, processed and remodulated onto a new carrier frequency. A high power amplifier boosts the signal, which is then transmitted back to earth through satellite transmitting antenna. This process ensures that communication signal are reliably relayed with maintained quality and integrity. Then we have ground segment. There we have earth station, right. In ground segment we also have TTC subsystem for telemetry, tracking and command. Then we have user segment. In user segment we have satellite phones and satellite modems. Satellite phone provides voice and data communication, whereas satellite modems enables the data communication. In user segment we have VSATs, and VSATs stands for very small aperture terminals, a small ground station used to two-way satellite communication, commonly used for internet access, telephony and data communication. Then we have mobile satellite terminals, broadcast satellite receivers in user segment. Then we have another component of satellite communication architecture is link segment. In link segment we have uplink and downlink. So, why uplink and downlink are differ in frequency? Because to avoid the interference. So, uplink is normally kept at the higher range, because in ground it is easy to generate the beacon signal, we can have a complex circuitry, and at the satellite and the downlink is a bit lower frequency, because a bit complexity is reduced if the downlink is less. Then we have another segment of architecture, that is communication network. So, in that we have terrestrial network interface, then satellite gateway station, then network management system and data processing centers that facilitate and process and manage the data transmitted and received via satellite communication. Then we have different frequency band that is used for satellite communication. One is C band, that is 4 to 8 gigahertz, then Ku band, that is 12 to 18 gigahertz, then Ka band, L band, S band. Each band, right, has a specific frequency and it has a specific use. L band is specially used for GPS. Then another segment is modulation and coding. We very well understand what is mean by modulation. Here QPSK, quadrature phase shift keying modulation, BPSK, and especially 16 QAM is used for satellite communication. Then another segment of architecture is MA, that is multiple access technique. So, in multiple access we have TDMA, time division multiple access, FDMA, frequency division multiple access, and CDMA, code division multiple access. Then another segment of architecture is protocol and standard. We have various protocol and standards for satellite communication, that is DVB -S oblique S2 oblique S2X, that is digital video broadcasting in satellite. Then we have IPOS, that is IP over satellite. This protocol that enables the transmission of IP data over satellite link supporting the internet and data services. So, these are the essential components of satellite communication architecture. Thank you.